So for our first example, we're going to do an induction problem. So use induction to prove that the summation from 1 to n of 4i is equal to 2 times n plus 1. So remember, when you're doing induction has two parts. So there's the basis step, and here we're only going to talk about regular induction. We also did strong induction, which but these two steps are the same in both, and there's the inductive step. Okay, so let's start with the basis step. The basis step is where you prove that the formula is true for your initial value. So here, the smallest value that n could be is 1. So that's going to be our initial value is n equals 1. So if I plug in n equals 1 into the left side, there's only one value I could be, which is 1. So it's not really a summation anymore. It's just the number 4. Now if you plug in 1 into the other side, 2n plus 1, if you plug in 1 in place of there, you'll get 2 times 2, which is 4. And those are equal. So we know that this formula is true for n equals 1. So now let's do the inductive step. Let k, we need an arbitrary value that's at least as big as our basis step. So let k be any integer that's at least 1. And you're going to assume that the formula is true for k. So replace n by k in your formula. And now you want to show the formula is true for the next value, which would be k plus 1. So now we're going to look at this summation. So here you're adding up a bunch of stuff together, and what you're going to do is you're going to peel off the first k, the last term. So I'm separating out when I is k plus 1 into a separate term. And now for this thing right here, we can use our formula right there. So this becomes 2k, k plus 1, and so you need to factor out a k plus 1 out of both of these. And you can actually factor out a 2 as well. So then in the first one, you'll be left with a k, and the second one, you'll be left with a 2. And if you look back, that's exactly what we needed to get to. If I go back to my formula, replace n by k plus 1, and this is exactly what we needed. So we have reached the end of our proof for the inductive step, which means we're done with the proof by induction.